But let's talk about work and uniform circular motion. Okay? So in order to talk about that, we first need to start with dot products. But before we even talk about dot products, let's talk a little bit about vectors. And we're just going to kind of give let's write out the whole thing. Work and uniform circular motion. All right, and in this work and uniform circular motion, we need to know about a couple things. So let's talk about dot products. And again, like I said, in order to know about dot products, let's talk about vectors. Vectors are usually, well, let's start with vectors on a Cartesian coordinate plane, right? Vectors have two things. They have magnitude and direction. So let's say if we wanted to have a vector A that looked like this. Let's get some colored chalk, huh? We never do anything with color anymore. Let's see here. What are you thinking? Red, maybe? So we could talk about the y component of A, AY. And we can talk about the x component, AX, right? So basically, on this part of the x-axis, the length of it will be AX, and this part of the y-axis will be AY. This length on the y-axis will be AY. So we need two coordinates to describe a vector, usually, unless one of them is 0. But the big thing about it has a magnitude and direction, okay? So the magnitude is usually given by the Pythagorean theorem. If we wanted to have we want to have a vector that looks like this, right? Where we have, so let's write down this vector, I should say. A is equal to, get my chalk back out, AX I hat plus AY J hat. Okay? How are those colors? Okay, good. Colors are good. This is legible on this type of angle. Now, with this vector, what we can do is a few things. So in each of these components, we have a magnitude and a direction. So the magnitude AX is associated with the I direction. That's usually what we call the x-axis, and then the J direction is usually what we call the y-axis. Okay? Now, inside of these, this is what we call a unit vector. Okay? Now, a unit vector has the following magnitude and direction. It has a magnitude of 1. Whoops. Magnitude of 1 and a direction along an axis. So for instance, this I hat direction has a direction along the x-axis. That means all of the other components are 0. Correct. Okay, so they have a magnitude of 1 and they have a direction along the axis. That's what these are, I hat and J hat. And they are literally just to tell you what direction that magnitude is in. So AX is in the I hat direction and AY is in the J hat direction. Okay, now, that's enough. That's really all we need to know for the vectors. Because then the next process is to say what a dot product is, okay? So the dot product is denoted with a dot. And it's one of the two ways you can multiply vectors together. There's more than 2 ways, but we're not going to get into a lot of them. They're a little bit complicated. It all has different meanings at different levels of physics, but we're just going to stick around with the dot product for now.
Weird.
As one of the two main ways of doing vector multiplication. Thoughtful Neanderthal, welcome to the channel. Thank you. Now, I'm going to give you the baseline definition of it, mathematically. We have a magnitude. That's how you denote magnitude. You put absolute values around it. Let's not do another dot. The magnitude of A times the magnitude of B times cosine theta, where theta is the angle in between the two vectors. So you might see something that looks like this. You have some sort of axes. You might have, we're going to go back to blue and, actually let's change it up because I don't want to use the same ones. Let's do green and orange. Might have some vector B and some vector A. And they might be separated by some angle theta. And the definition of the dot product, we'll say definition, is...
Use the purple rain chalk.
Purple rain chalk? I'll save the purple chalk. Maybe we'll do something later with that. I haven't, maybe. But another way we could write about it is, what happens if we wrote out the entire vectors, much like this, and then we FOILed them like you might do, or distributed them. So let's do that as well. So let's see, A is equal to AX I hat plus AY J hat dotted with BX I hat plus BY J hat. Okay? So writing all that out, we can do that. That's easily. We just wrote out those two vectors. Oh, yes. You'll see. You'll see, Dodo. You'll see. So then if we distribute these, or FOIL them, FOIL is first, inner, outer, and last. That's just a way of distributing. We'd see we get AX, BX, I hat, dot I hat, where the dot product goes through on the unit vectors, plus AX, BY, I hat dot J hat, plus AY, BX, J hat dot I hat, plus AY, BY, J hat dot J hat. Now, looking at our basic definition, looking at our basic definition of the dot product, and knowing what we know about unit vectors, i.e. the unit vectors have magnitude 1 and direction along the axis, we can figure this out relatively simply for them, right? So I hat is the first one. That just means our magnitude of the one vector is 1. Our magnitude of the second vector is 1. And the angle between the two, from the I hat to J hat, is always 90. Cosine, I hat, excuse me. I hat. I went too fast. So I hat to J hat's always 90, but I hat to I hat's always 0. So cosine is 0. Cosine of 0 is 1, so this whole thing is equal to 1. Okay? Eric is eternal. Nice. Okay, so then what about I hat, J hat? I hat, J hat. Well, then we have the same thing for our magnitudes. Magnitude of I hat is 1, magnitude of J hat is 1, and the angle between the two is cosine of 90. Cosine of 90 is 0, so this is always 0. So basically, anytime you have vectors that are perpendicular, now this is the part where it, Hi, born math professor. Thank you, Russian guy. Yes, that's the only use for it. But the big point is when I hat and J hat are dotted together and they are perpendicular to each other, it makes a right angle. That is always 0. Okay? Yes, cosine 90 degrees, or pi over 2. Okay? 90 degrees is pi over 2. All right. Now, is that what we need to know at the, well, we can finish this dot product here. So then if we let this go to 1, this and this go to 0, and this go to 1, we'll just get that the dot product, another way to write the dot product is like this. And it's just AX, BX plus AY BY. And as long as we can write the vectors as a sum of their unit vectors, and the unit vectors are all perpendicular together, then this is all what we're going to get, which is usually what you find in Cartesian coordinates. Okay? Now, what's the relevance of the dot product? Well, the definition of work is a dot product. So let's get to the definition of work. I should probably keep the definition of the dot product somewhere so that we have it. So let's rewrite it really quickly up here. So A dot B, and now I'm going to write you can write the magnitudes in a couple ways. This is the other way. It's just A, B, cosine theta. It's easier if we do it like that, okay? So now, let's say the definition of work. Work is equal to the integral of force dotted with ds. Or, if you don't want to do the integral, we could say, as long as the force remains constant, we can say F dot delta R. Okay? So as long as the work remains constant, it's just the change in distance. Right? Work requires a change in distance. Now, I think this is kind of where we start to get into some issues, especially with uniform circular motion. Because, I don't know if you guys noticed or not, but things in uniform motion are moving, right? They are moving. So how do we reconcile this motion with work when we know that the work in uniform circular motion is 0? Well, we can consider, and then basically what we'll do is we'll consider two options. So the first one we consider is horizontal. And then we'll do vertical, because that was what the question actually was about vertical motion. So, in horizontal motion, let me move this. I don't want to break this. Okay. In horizontal motion, so let's get some horizontal circular motion here. Now, if this was truly horizontal, so just pretend it's truly horizontal. I don't want to make it truly horizontal. I don't want to break anything, so we're going slow. Truly horizontal would mean I'd have to go faster, and I don't want to do that. But now again, you'll have to kind of use your mind's eye for this, because this is some different stuff's going on, because we know that it's down lower. But for instance, if it's truly horizontal, then we have the ds, well, let's just say, we'll use ds. ds, infinitesimally small change in direction, is this way, right? The motion, the change of the displacement is this way, but the force is this way, right? So I don't think anybody's arguing that when you have that, we have force. The centripetal force dotted with the change in r is always going to be F delta r cosine theta, where theta is 90 degrees. If cosine of 90 is equal to 0, if cosine of 90 is equal to 0, then this whole thing goes to 0. Okay? That's fine. But now, what happens if we look at the horizontal picture of it? Okay? So suppose this is the horizontal orbit. Okay? Now again, we're going to have some change in ds going this way. Let's use purple. Some tangent. Purple looks like white to me. It doesn't look like purple at all. But we'll have some, some displacement change that way. Delta x and ds. One is infinitesimally small and one is just the sum of small points. Actually, to be honest, for all intents and purposes, Dodo, this does just mean the change in distance. So like me walking this way requires some work, right? Because I'm applying a force this way, right? Pushing this desk, I'm pushing this desk some distance. That distance is delta r. Okay? That's all. And we call it displacement because vectors have vectors, a displacement vector means I'm pushing it this way, this far, and this direction, right? Yeah, and ds is just doing that, but at infinitesimally small steps. You need calculus to understand that one. That's for like the next step up. But we are going to use this to show more about what I'm talking about. But this is just a general idea, okay? So then from here, if we want to talk about the force due to gravity, so now again we have the displacement going this way because it's uniform circular motion, so we pick the tangent. So imagine this just flipped on its side and put here, okay? So now the displacement is going this way and the force due to gravity is going down. This is again for horizontal motion, okay? And I would, like I said, I would do it a lot more dramatically, but I don't want to break anything in my office. Okay? So those are the three things happening. We have a centripetal force, which is causing tension on the string, and we have a force due to gravity, which is pulling down. But as you see here, all of these angles are 90 degrees. So anytime you take the dot product here, and you take the, you get the actual dot product definition, you have a cosine of 90, they're all going to be 0. So work is always going to be 0 in a horizontal motion. But now the question that Dodo posed was, what about vertical motion? And then we have a little bit of a different situation. I can just go to the other side of the board. Why do we have a little bit of a different situation? Well, because the centripetal force is going to be the same, sure. Okay, the centripetal force in vertical motion is going to be the same. Right? There's still going to be some centripetal force going towards the inside of the circle. Let's tighten it up a little bit here, huh? Ah! Right? And then, what happens though in the vertical thing? Because now there's parts of the orbit where this is not perpendicular, right? So let's talk about that. So now let's look at the vertical loop. This is still true, but now what instead? Actually, let me make that a little bit better. A little bit better of a circle. But now we have some distance like this. But here, notice that this is equal for the force of gravity, but it also describes the displacement. What about right here? Well, here, this is the displacement, and this is the gravity, force due to gravity. And then here, this is the displacement, but here's the force due to gravity. So what does that mean? Okay? Well, let me just tell you. That means that every single point along this axis, there's something, the angle theta is going to be changing, the theta between the 2 points. Okay? So we have to figure out what that is. Okay? So let's talk about let's talk about this, the work as an integral, okay? And Dodo, just kind of pay attention. You don't have to pay attention to all of the integration. So you don't need to pay attention to each step of the integration. Instead, I'll kind of explain the whole, what's going on in each step as we go, okay? So what's going on is we have the integral of work is equal to the integral of the force dot ds, okay? And what we're going to show is that in uniform circular motion, we'll end up taking care of all of that, okay? So let's do that. Now, if we were to have if we were to actually set up the bound to the integral, we can start up here and say that displacement is like this, and the force due to gravity is like this, and then the ending point is going to be down here, because we're just going to take this half here, okay? The ending point will have the force due to gravity here, and the ds will be right here, and we'll have this is 90 degrees and this is 90 degrees, but they're flip-flopped, so we need to have 180 degrees of separation. So what I'm gonna do is take the initial to be pi over 2, because we want to project ds onto FG, so this is going to be here, but then this upper angle is going to be 3 pi over 2. And I know we have ds here, we got to change that. I'm just kind of getting my bounds out in the open right now, okay? So what we're doing here is we have a projection of 90 degrees onto here, but in this case, if we want to project ds onto f, we got to go all the way around the 3 pi over 2, okay? So we're projecting this because we want to project in the same way. So we're going to project this way. So that's our bounds, pi over 2 to 3 pi over 2, okay? So let's unpack this a little bit. So now we'll have our bounds, we'll have f ds cosine of theta, and we know we want to integrate over theta because the theta between the vectors is the thing that's changing as you move around the circle. So let's get it in terms of pi over 2, pi over 2. So how do we change this into an integration variable for the angle? Well, we can talk about arc length. If the radius is r, the r is not changing. But what is changing is theta. So ds is going to equal r d theta. If you were to take the derivative with respect to theta, you'd get ds d theta equals r. Hi, Sarah. Good to see you. So then what's going to happen is when we plug in the ds up to here, we'll get the integral, and now our bounds actually make sense. Boring math professor is probably cringing at my bounds. I'm sorry. We can actually say what the force due to gravity is. It's just mg. That's not going to change. R is not going to change. And we'll get cosine theta d theta. Okay? And then what's going to happen when we integrate this? Well, what's the integral of cosine theta? It's minus sine theta. Wait, no, it's not. It's just sine theta. Whoa. It's just sine theta. Gotcha. So then it's going to be mg r sine theta over the integral of 3 pi over 2 and pi over 2. So how do we integrate that? Well, now we're going to plug in these values. And I'm going to show you, and now this is the part that to really pay attention to, Dodo. What we're going to get here is mg r minus 1 or negative 2 mg r. Okay? Now, if we take the height of the circle to be the diameter, right? If we take the height, I gotta erase this side. It's just the horizontal action. If we take the height of the circle to be the diameter, diameter equals 2 times the radius. So our work is now equal to, we had minus 2 mgr. So it's minus mg times the diameter. The diameter from here to here also happens to be the height. So this is minus mgh. This is what you thought, Dodo. This is what you thought was happening, right? We have this extra energy if you just go from the top to the bottom. Right? We get this extra potential energy of mgh if you go from the top to the bottom. That's the work done from going to the top to the bottom. However, this is not uniform circular motion. Right? That's the point. This is only half of the uniform circular motion. And that's what I was talking about in Discord when I said you can't do snapshots. You have to do the whole thing. So if we wanted to do the rest of it, what would we do? Well, we would just go back from 3 pi over 2 to pi over 2. We would sum the works together. Work of 1 plus work of 2. If this was the first half of the work, if that was work 1, work 2 would just be the opposite sign of that, which would be minus mgh plus mgh. We get back to 0. So that's basically what I was saying, Dodo, is when you consider uniform circular motion, the work from the one half to the bottom half, that's true, that's not conserved. Like, that's the issue with the vertical motion, right? Is along this way, this work at each and every one of these snapshots is not necessarily 0, okay? But then, by the time you make it all the way back up to the top, it is. So the difference between what Tyrion and I were talking about on your Discord is Tyrion was saying you can't have uniform velocity because if you're not acting on it with another force, right? And instead, what I was saying, is yes, you can have uniform velocity, but you need to act on it with another force. So like, for instance, if I want uniform velocity like this, then what do I need to do? I need to be driving it, right? I need to use my arm muscles to drive the ball up, and then I'll use less muscles on the way that it goes down. That way I'm consistently I'm driving that oscillation. And that's the difference between what Tyrion and I were saying. Tyrion is saying without that driving motion, you won't get uniform velocity. Either way you look at it, work is conserved. So that mg sine A is balanced when you drive it. Yes. Yep. So like I said, for this side, we would not be driving it. We would be letting it fall more, or like driving it less. And then here we'd have to drive it more, and then drive it less, and then drive it more. But in the end, the work done is the same. So I'm glad that makes sense. Now I gotta get caught up on chat.